So we just start discussing on the binary search tree part. I hope you guys, we just start discussing on the graph, which is, looked it up, this is chapter 16. Just before this, we did discuss on the binary search tree and different type of, different type of operations that can be performed on top of binary search tree, right? Insert, delete, search. Of course, in order to do any of the insert or delete, you need to do, you need to know how to do a searching. I'm thinking about asking you a similar questions for those part. For example, writing a pseudocode or a coding style, C type of coding on your final exam. I haven't decided yet, but there's a high chance that I will ask you to write it. That's for the tip of those people who's early in this morning. 여기 오늘 일찍 온 사람들에만 주는 힌트. 아마도 내가 그 인서트지, 서칭이든지 바이너리 서치 트리에 아마 그런 중에 하나 아마 코딩하는 걸 물어보지 않을까 그럴 것 같아요. 뭐 수도가 될지 아직 그까지는 잘 모르겠고요. 수도 스타일에 될 것 같고. 우리끼리만 합시다. 늦게 온 사람들한테 얘기해 주지 말고. That's the 그 일찍 온 사람들을 위한 하나의 팁. So that's a tip just between us. And then I will stop discussing this problem. So hopefully the basic things that you need to know is the time complexity as well on the binary search tree. Make sure you know how to do it, how to construct a binary search tree. Because we cover heap, you might be confused with the heap later. So constructing a heap, constructing a binary search tree, you need to practice separately at least once. 힙하고 나중에 그리다 보면 힙 그리는지 바이너리 서치 트리 그리는지 좀 헷갈릴 수도 있으니까 꼭 헷갈리게 돼요. 한 번 정도는 안 해야 될 거 하고 있고, 그러니까 한 번 정도 그려보면 I hope it will be better for us. Okay, then we move on to the graph part. This chapter actually covers general aspect of all graph. Some of the mostly terminologies, vocabularies that you may not be familiar with, definitions of different properties of a graph. So let's begin just looking at some of the very basic terminologies. I did discuss this Monday, but reminder, graph terminologies, vertex. I also told you I usually call it at a node or dot, whatever you want to call it, but to be exact, it's a vertex. Edges, any lines between the vertex, so any lines between the node. They could have directions or they could be bidirectional, so it could go both ways. Trees that we've been drawing so far, does it have any of the directions? No, right? So trees, at least the trees that we have seen so far, didn't have any directions in it, so it could go both ways. Adjacent, simply put, there are two nodes or two vertices. Two vertices are connected together, sharing a single edge. Then those are the adjacents. Another way of saying is neighbors of each other. You have a two dot connected by the one edge, then it's adjacent to another. 나중에 나오긴 하는데. Anyway, another way of saying it is neighbor of each other. Incident. You have a single vertex. You have edges coming in and out. If, of course, it's a bidirectional, it's not coming in and out. Just sometimes counting how many edges that you have in your vertex. That is quite similar to the degree, no degree that we've been discussed, right? It's a degree as well. Cycles. I did discuss how do you define a cycle if given a path? What was the idea for defining a cycle? Finding a cycle. 뭐였지? Well, path is a sequence of vertices, right? Path usually my path is going to be 3, B2. Something like this. I'm proceeding this way. I see myself again in the path. So encountering the same vertex one more time. It's the same thing as in the, well, V1, V3, V2, what? Cycle, right? I'm saying one of the vertices one more time. The vertices that was already exist in the path. Right? Path simply the sequence of edges, so it goes through a vertices. And connected component and spanning tree, we will discuss that in few slides after this. Type of graph, undirected, directed, and weighted. Directed. 아이고 이렇게 하면 좀 헷갈리겠다. 뭐 이거 다 아는 거니까. Undirected, no direction. If I start drawing a direction, directed. Weighted. What was weighted? You guys know this because we covered this extra shortest finding path algorithm in Introduction to Computer Science. What was weighted? Weight. weight가 뭐였어? 아니야. weight. weight. 이거 아니야. Or we call it as a cost too, right? If I start writing like this, is from node A to B, it costs 10. Weight, also 무게, weight. Another way of saying cost is weight. So it's a weighted graph if I start writing like 5, 10, 20 between each other. It's a weighted graph. 그래, 이거는 이해합니다. 왜냐하면 나도 뭐 저기 뭐 영어가 모국어는 아니니까 웨이트랑 웨이트랑 발음이 잘 구분이 안 되는 거 나도 이해합니다. So weight is another way of saying cost in the tree. Graph representation, again, adjacent matrix is adjacent array, adjacent list, linked adjacent list. Like I say on Monday, in order to describe this graph on your program, how you design your data structure. What kind of data structure would you use to represent this in your program? Well, first thing you should consider is maybe you always have two options. According to any other data structure that we have seen in our textbook, they usually first try was they wanted to use the array first. Yeah? And then they come up with some ways. And then they also show you another approach using a linked list. And they usually compare the time complexity of each, which one is better than the other in terms of time and space complexity, blah, blah, blah. Same thing. We might be able to use an array-based representation to represent this type of graph or linked list. 뭐 어떻게 하면 되지? How would you do it? How would you do it? How would you implement this? 어떻게 하겠어? If I ask you a programming question on implement this tree and give me the path between V1, this is just too small. Implement this, give me the path information, all possible path between V1 to V4. Your program should report me all possible paths in between. 어떻게 하겠어? 구현 어떻게 하겠어요? 일단은 패스를 구하려면 이거를 프로그램 안에 집어넣어야 될 거 아니에요, 메모리 안에. 데이터 스트럭처 어떻게 가져가면 좋을까? Any suggestions? Of course, they would give you answers later. Last final slide, they try to give you different ways of doing it. 뭐 가장 뻔한 게 뭘까? 배열? 배열이 뭐지? 어? 배열이 뭐? 배열이 뭐야? 어레이. 미안. 아, 배열이 어레이야? 미안합니다. Array. Yeah, I mean, okay, let's go to the array part. How do you use array to implement this? Array is just too big. 어떻게? I don't know. So you're discussing matrix. Matrix. Array of array, 그죠? Array. Okay, that might be the one. Or if I wanted to use just one array, maybe I can record my neighbors. V1 is neighbor of, this is V1, V2. This is my linked list to V3, V2, neighbor of V1, V3, V3, neighbor of V1, V2, V4, V3, something like this. Maybe something like this might be helpful. I don't know. Or dumbest way might be doing everything as a linked list. But I don't know how many pointers will I have because there's no restrictions. 이거 링크 리스트로 노드 구현하면 어떻게 해야 될까? 링크 리스트로 노드 구현하면 얼핏 생각하게 포인트 2개. 이거는 근데 2개니까 문제는 엣지가 몇 개가 나갈지 잘 모르지, 그죠? 엣지만큼 만들어졌는데 뭐 그래프. 여긴 지금 we're discussing an all graph, so it could have many number of edges. So do you want to change the data structure class definition every single time you have a new edge, or do you need to find other ways to describe it? So there might be a bunch of different way of implementing this to a structure. Well, this might be one array of array matrix representation, like B1, B2, B3, B1, B2, B3, B4. If they have a pointer, if they are pointing to each other, maybe this is 0. V1 is connected to V2, so I'm going to say 1. V1 is V3, 1. V1, V4, no. So I might say just 0. Or if I have a weight, then I might be able to put a weight on it. Then it's an array of array representation. So I could just simply implement that. Next time, if I want to compute anything, maybe I just look at this matrix in your program to whatever, compute the cost and different stuff. So there might be a few other ways of implementing this graph using a different data structure. So I guess in order to implement this graph, you need to think of all the structures that we have covered so far. 대충 지금까지 했던 모든 데이터 스트럭처가 어떻게 되는지는 막 머리가 복잡하죠? 이것도 혹시 Q로 할 수 있나? 라도 생각을 해볼 수도 있고 Q로 되나? Q로 하면 알려주세요. 나 Q로는 할 줄 모르겠어요. 뭐 여러 가지 머릿속에 있는 데이터 스트럭처 갖고 이제 조립을 하기 시작하겠죠. 그죠? 몰라 어떤 게 제일 편할지는. So they will give us a few propositions on maybe adjacent matrix way of implementing this, or array adjacent list, or linked list adjacent list, neighbors list, neighbors. So once you figure out how you're planning to do this, this way, or any other way, then coding is not a problem. Programming is a piece of cake after this point. Or hopefully there is already ADT exists that you can use to make a graph in it. Already things are implemented, hopefully. So graph search algorithms. So you have a graph now. Like those are previous tree example, binary search tree or heap. Once we construct a graph or tree, then next thing we usually did was try to find the element in that tree, right? That is also another way of searching a node in the graph. I'm looking for a node with that certain values, right? Binary search tree search 뭐했어? I'm looking for a node with that exact value or less than equal to, stuff like that. So, same thing. So it's breadth first and depth first is another searching method, but in generalized graph. So we would take a look at it. 근데 잘 안 나오더라. We would take a look at it if we have a chance, but it's a bit outside of the scope. This will be covered in probably algorithmic courses in next year for you guys. 컴퓨터 알고리즘에서 아마 breadth first search나 depth first search는 그때 나올 거예요. So usually there are these type of algorithms on top of this graph to find the path in the graph, to find the connected components of an undirected graph. Now it's a graph. What if I remove this edge? What if I remove this edge? Can I get to 4? No, right? How do you determine which edge to remove, which edge to safe to remove, and I still be connected? Well, even if, okay, this one, let's not delete this. What if I delete this? Can I get to V3? Still, I can get to V3, right? So still be connected, although edges are connected. So what do you call that? How do you find the edges that is crucial for connectivity? 희한한 거 하는 사람도 많지. 평생 그래프만 갖고 노는 사람도 있다고 그랬었죠. That is another way of saying probably spanning tree, finding a spanning tree of a connected undirected graph. See what it means. Let's go one by one. I actually explained most of the concept in the first page. Let me just be a bit more careful with the definitions and stuff. 이거 다음 주엔 뭐 하지? 다음 주 월요일도 그래프는 어차피 해야 될 것 같고. 리뷰할까? 챕터 하나 더 나갈까? 리뷰할 게 없는데 다 아는 거잖아. 큰일 났네. 챕터 하나 더 나갈까? 아무 반응이 없구나. 리뷰에는. Graph. Usually is defined that G representing graph, V and E is vertex and edge. So G consists of vertex and edge. So that's a graph. That's how they actually write it. V is vertex set. So they usually write it this way. There's a small v for all v. All the vertices, all the node, it's a set of this. So all node exists. Same thing, edges too. All edges in another way of saying it like that. V is vertex set. Vertices also called node or points. I usually call it as node, so don't get confused. Even I don't say vertices, vertex. E is edge set. Each edge connected to vertices. So probably something like if EI, EJ, 어떻게 쓰는 게 맞나? Then it's probably a edge. 아이고 EI가 아니구나. VI, VJ, VI, VJ. It's a edge between the two. Edge is also called an arcs or lines. I usually call it edge. The vertices I and J are adjacent vertices if I, J are edges. If I, J are an edge in the graph. If node I and J have edges between them, I is adjacent to J, J is adjacent to I. Like I say, it's another way of saying it. J is I's neighbor, J is I's neighbor as well. It comes both ways. 왜 저렇게 복잡하게 쓰는지 난 잘 몰라. Adjacent, but I usually think of it if they connected, they are adjacent. The edge I and J, it's incident on vertices vertices I and J. 잠이 덜겠나 보다. Vertices I and J. So this edge is incidence of I, incidence of J. Okay, incident of J. 이렇게 붙어 있으면 incident라고 부르는 거야. edge잖아, 선, line. 읽어보면 the edge I and J are incident on vertices I and J. 이 선을 이제 I의 incident라고 부르고 J의 incident라고 부르고. 그냥 기본 지식 쌓아간다고 생각하는 챕터로 생각하면 돼요. 별로 계산할 것도 별로 없고 사실 이 그래프는 기본 지식 쌓아가는 거라고 보면 돼요. Graphs. Undirected edges has no orientation, no arrowhead. Undirected, this one has no head. So that's undirected. Directed, it has an arrowhead. Undirected graph, all edges are undirected. Directed graph, all edges are directed. So those are the two representations. So if you have a graph with all edges, then all arrowhead, then that's a directed graph, otherwise it's undirected graph. I think I take this course, similar graph course in my 언제 들었더라? Third year. 아마 3학년 때 처음 들었던 것 같아. And this part was covered about a week or two. They covered this 한 1, 2주 정도, 첫 1, 2주 정도에 커버했던 거로 얼핏 기억해. Undirected graph is that. Directed graph is digraph is like that. Quite easy. So directed graph, it is useful to have a slightly refined notion of adjacent and incidence. So it's one direction, so it's easy to represent a incident, and they could divide it into a couple more definitions. Directed edges in I and J is incident to a vertex J, incident from vertex I. Vertex I is adjacent to vertex J. Vertex J is adjacent from vertex I. It depends on which direction that it goes. You can say differently. In terms of undirected graph, it could go both ways. Now you can say if the edge is coming from I to J, then you can say it's an incidence from I to J. Vice versa. Depends on the direction of the edges. Why this is important in nowadays, you could look at it as your internet connections. Your internet connections. It's a slightly beyond the course, but we did discuss on some of the technology that used to connect the people, right? Internet is connecting the people. And in order to connect the people, there is devices everywhere that is connecting you to elsewhere. Something called routers. Router가 뭐지? How do you translate that router? What's a route? 이게 뭐지? What does that mean? 길. Router is a device. It's a computer that finds you. 짱인데 오늘 두 번 정도. Router is a device that finds you a route, path, 길. So, for example, our university, Hanyang University has maybe some big router, maybe 2 big router to go out of the Hanyang University network or go into Hanyang University network. So if you project everything internet, it's a graph. It's a graph. I might be in, well, this might be me. This might be some friends in US or Canada. So which path to take? That is also, if you abstract the problem, if you simplify the problem, then it's same problem of finding a path in that graph. Of course, it's much more complex graph, much more complex graph. I don't remember, I'm not so sure that you guys will remember the graph that I show you in the Introduction to Computer Science. There was some map of internet, very, very complex. I think it was looked like circle and 막 이렇게 될 거 있었는데. Anyone remember this? Let's say that's a graph, and using that graph, we wanted to find the path between the node. The thing is, we always to be connected, right? So even if I delete one of the edges, we still have another path to that certain node. 왜 인터넷 처음에 그렇게 디자인된 줄 알아요? 인터넷은 실제로 그림을 그려놓고 보면 다 연결된 것처럼 보여요. 막 다 연결되어 있는 것처럼 보여요. 그래서 아무거나 하나 끊어도 딴 길이 있고 찾아가려고 하고, 물론 이제 다 너무 많이 끊으면 딴 길이 없을 경우도 있지만, 근데 왜 그렇게 처음에 만들었는 줄 알아요? 그 내가 얘기했던 것 같은데. 그 전쟁 때문에 그랬다 그랬죠? 콜드워라 그러나? 냉전 때 인터넷 처음에 만든 사람들이 핵폭탄이 떨어져도 다 통신이 되게 만들고 싶어서, 핵폭탄이 떨어지면 진짜로 개념이 그랬대요. 핵폭탄 같은 정말 한쪽이 다 날아가도 계속 연결이 되고 싶어서 그런 개념으로 만들어서 했다 그래요. 그러니까 인터넷 처음 만든 사람들이 이런 것도 다 참고하면서 만든 거겠지. 그렇죠? So we could represent a vertex as a router, and the edges between is a communication path, or simply put as the cable. 이런 거 cable is also okay too. Easy way to say it. And each path has a different path, different cost. And this one is representing a city. So if you project the internet in terms of city, then Seoul is one of the big routers. Busan also big router. You could go to some other countries, but the cost of going from Seoul to Japan or Busan to Japan will be different because of perhaps the physical distance as well as other factors. So you could have it like this: 2, 4 edges, driving distance, time. So from 1 and 2, it would take 4. 2 to 5, 8. So one of the algorithms that we have to take a look at it, they usually wanted to find the minimum cost path between the two vertices, right? Whatever that means. Driving distance, time, and map. I am doing this in my head every single morning that I'm driving from my home to the campus. 그지? 여러분들이야 대부분 다 대중교통 이용하니까. If I sometimes bring my car, I have to think which way is faster according to what time that I'm leaving my house. So there is at least 3 different paths to come down here. So I'm doing this doing the same thing in my head every single morning. Or sometimes the navigation is doing for me. 내비게이션에 구현되어 있는 게 다 이런 거겠지, 사실 기본은. 그렇죠? 내비게이션을 안 쓰시니 얘기를 할 수가 없고. 내비게이션이 뭐야? 내비게이션에 네이버에서 길 찾기 같은 거 하면 나 어디서부터 여기 가고 싶어, 점 찍어줘가지고 걔네들이 가지고 있는 점 중에 가장 가까운 길 찾아서 하는, 기본은 다 이거예요. 다 그래프예요. 다 그래프. 이제 내비게이션 만들 수 있겠다, 그지? 내비게이션 구현하려면 이것도 해야 되잖아. 이것도 해야 돼, 저것도 해야지 구현을 할 거 아니야. 프로그램을 할 거 아니야. So these are the application street maps from one way to another way. But in some cases, streets are one way only. 일방통행. If you want to represent a one way, then directed graph might be one of the options. So only from 1 to 4 you can go to one direction from 1 to 4. You cannot go to 4 to 1 directly. You might need to find a different path from 4. Let's see, in order to go to 1 again, I guess from 4 I cannot go because it's only one way. 2-way may be a directional, about undirected graph. A single directed edges denote one-way street. Two directed edges denote a two-way street. If you take a look at the books and figure 16.2a, they try to explain that, but it's a dumb example. Don't worry about it too much. Sequence of vertices. Sequence of vertices, that's a path. I referring to any vertices. So Pi1 to Ik is an I1 to Ik is a path in the graph in G if and only if the edge Ij and Ij plus 1 is in E for every J, J is between 1 to K. It's a very simple way of saying it. If I have a K node, the index should be between 1 and K. All number of nodes is K. Index should be between 1 and K. And the sequence of nodes should be I, J, and J plus 1. 똑같은 얘기 그냥 반복해서 쓴 거예요. So can you, with this definition, can you find a path for a given graph? It says 16.2b. Just draw 16.2b here. 거의 뭐 IQ 테스트 수준이지 뭐. 간단한 IQ 테스트. 1, 2, 3, 4, 5, 6. Go up, go up. They did the strange ways, but it's not a good way of doing it. They probably, this is better. Finding all paths in this figure. What are the possible paths on this figure? Any I and J? 그냥 다 하면 되지. 4, 1 is one path. 4, 5, one path. 4, 5, 6, one path. Yeah, someone stop me at some point. 2, 1 is one path. 또 뭐야? 4, 5, 2. 4, 5, 2, 1. 4, 5, 2, 1. Blah, blah, blah. It's all the possible path in this graph. 그치? It would be interesting to give you programming exercise like report me all the possible paths and tell me which path is safe to delete it. 그럼 어떻게 해야 돼? Question might be, given all the possible paths, tell me which path, if I delete which path, the graph will be disconnected. Something like that. That is something that you should be thinking of on doing it. What about the simple path? Another definition. Simple path is a path in all vertices are different. Paths all vertices are different, except possibly first and last 1. So if I have some path, 뭐 있을까? 2, 5, 2, 1. Is this a simple path? Is this a simple path? According to the definition, just apply the definition. Simple path, let me read it again, is a path in which all vertices are different. 아니죠? Well, I have, it's not. So maybe things like 뭐였냐? 5 to 1. Simple paths, all paths are different. So all vertices are different, I'm sorry. But they also have an exception. The first and last element could be same, right? So if they are same, it's a cycle. We'll see. So another simple definition. Path, simple path. 그지? Path and simple path. Cost of the path. easy. As you go along these vertices, you add it up. 그죠? Each edge in the graph has associated lengths or cost. The length of the path is the sum of the lengths of edges. Length of the path is the sum of the lengths of the edges on the path. What is the length of the path 5, 9, 11, 10? 너무 쉽다. 5, 9, 11, 10. 4, 8, 3. That's 15. Can you find another path with a different cost? More enough. You could go 5, 9, 8, 11, and 10. That's not 8, 13, 16. 아유, 암산도 안 되네. 16. 그렇죠? Yes, same. Length and weight is the same. Sometimes they want some cases they want a minimum length. Some cases they want maximum length. That depends on the problems. With also same meaning of saying a minimum cost or maximum cost between the two nodes. 나도 왜 이렇게 여러 가지 단어를 부르는지 모르겠어요. 그래서 다 알려주는 거예요. 여러 사람들이 부르는 단어를 다 그 분야마다 다 자기가 부르는 단어가 다 틀려서 뭐 vertice만 해도 노드, 포인트, 그렇고 뭐 엣지만 해도 많고 이것도 뭐 length라고 부르기도 하고 cost라고 부르기도 하고 어디 가면 weight라고 아까 돼 있었죠? weight. So it's the same thing. Then what is a subgraph? What is a subgraph? The name speaks itself. Subgraph. Let G be a VNE, be undirected graph. A graph H is a subgraph of G if and only if its vertices and edges are set of a subset of those of G. 뭐야? What does that mean? 부분, yeah, 부분. We already seen a subgraph in the three examples. What was the simple algorithm to when you try to delete and no degree 1, no degree 2 elements in the binary search tree? What was the simple pseudocode for those part? 그러니까. When you try to find a replacement for the deleted node, what was it? 어저께 한 거 아니야? 월요일에 한 거 아니야? I think you go into the left subtree, left subtree, and try to find the largest one. See, at that point you already cover subgraph, right? Left part of the tree is subgraph because tree is it's also graph too, right? So right subtree, left subtree is a part of graph. So simply just saying that subgraph should have all the vertices and edges of original graph. Okay, some part of the graph. The cycle is a simple path with same start and end vertices. It's not just any path. Cycle is a simple path. Again, definition of simple path is all vertices are different except the first and last one. Like it says, if all the vertices are different in the path and it starts from the same vertex and ending in the same vertex, that's a cycle. That's how you detect a cycle in the graph examples. Try to come up with the cycle detection program. 어떡하지? Yeah, one of the dumb approach, you come up with all possible path, but if it has a cycle, then it would never end, right? So you should come up with certain stopping conditions. So your program should be try to find all possible simple paths in the graph. Among all those simple paths, you're checking for anything that matches from the beginning and end vertices. If you try to write a program, what might be the time complexity of those parts? What might be the time complexity of finding all path? Why is it V? In terms of n, let's say that n is number of all the vertices. Huh? Cycle detection algorithm. Easiest way I can do, I cannot think of any linear way of doing it. I think there's only n square, because in worst case I need to go from single node to every other node. That comes to n times n minus 1, right? Worst case, of course, worst case. That gives me n square. There might be a better cycle algorithms out there, but that's the one thing that I can just think of now. If you find a better time complexity algorithms, then please give it to me too. 이러니까 재밌지. 막 그래프만 있으면 평생 머릿속에서 빙빙 도는 거예요. 이거 조금 더 낫게 할 수 있는 알고리즘이 없나. 근데 stop searching or stop try to implement on yourself. Algorithms are out there. Just find one that suits you the best. It says list all the cycles of graph 16.1. 16.1, it looks to be a bit dumb, but only thing that I can look at is start from 1 and back to 1. That's all the cycle requirement. 그죠? What is spanning tree then? What is spanning tree? I explained briefly at the first slide. What is spanning tree? Different definitions come and go on and on and on. Spanning tree. Let G be a graph, undirected graph. A connected undirected graph contains a no cycle is a tree. Tree with a cycle? No, we never seen a tree with the cycles in it, right? So connected undirected graph that has no cycle is a tree. Can you get to any other node, every other node in the tree? Tree is all connected. If you're in the all nodes are connected. From here I can go anywhere. From here I can go anywhere. So every possible pairs of the vertices are connected in a tree. So that's a tree definition. Another way of looking at it. Connected undirected graph that contains no cycle is a tree. A subgraph of G. So some graph of G, subgraph, contains all vertices of G is a tree, is a spanning tree. Simply means then if you can find the subgraph of some graph that connects every vertices in the graph, then that is called a spanning tree. 쉽게 얘기하면 그래프가 이렇게 있는데 지워도 다 연결이 되는 애들 다 지우면 딱 걔만 남잖아. 뼈대만 남잖아. 다 연결되는 그게 spanning tree. 그게 spanning tree. 나중에 나와요. 여기 example 나와요. 내가 이렇게 보여줄게. 찡그리는 사람들이 몇 명 있는데 보여줄게. 그래 뭐 이거 하자. Okay. This is my graph. This is my graph. Let's say, just given any graph. I'm not so sure this is right graph. What is the spanning tree of this graph? 방금 했던 거지. Trees. I only need 1, 2, 3, 4, 5, 6 edges to connect everything, right? 어디? 아, 여기 미안. 아, 또 그런 건 또 열심히 보네. 평소 때는 틀려도 보지도 않더니. Spanning tree. So often tree become a spanning tree of a graph. Spanning tree. So definition. Yes, spanning tree is not a unique. There could be many spanning trees. That's what's coming next. Sometimes they wanted to have a spanning tree with the minimum cost, if it's a cost tree, weighted tree. So, 예, 맞습니다. 꼭 하나의 스패닝 트리만 좋은 질문. 꼭 하나의 스패닝 트리만 있는 건 아니고 여러 가지가 있을 수 있습니다. So spanning tree has a n vertices and n-1 edges. n vertices and n-1 edges. 뭐 꼭 하나만 연결하니까 why n vertices and n-1 trees? I usually look at it. 난 저런 거 보면 이렇게 생각해버려. 그냥 단순하게. 난 멍청하니까 단순하게. Spanning tree only keeps the edges that connect all the node. So it's not so much different from having a graph like this. N node, and n-1 edges. It's also a spanning tree too, right? I can get to any other node. That's what it means. Spanning tree, n vertices, and -1 edges. n이 뭐냐? 하나, 둘, 셋, 넷, 다, 여, 일곱. 7 node, 6 edges. Good. This spanning tree examples, they try to give you another way looking at it. Spanning tree, what are the possible spanning trees for this tree? What is the cost of each spanning tree? In your textbook, they actually give a nice representation of a different tree. They actually give you at least 2 spanning tree of this. 이거 아니다. Slightly different graph. But maybe I can draw it apart. 이거 뭐 어떻게 그리면 될까? How do you determine a spanning tree? 난 잘 모르겠고 얘랑 얘는 절대 끊어주면 안 되겠죠. 끊어주면 얘는 전혀 길이 없으니까 뭐 그런 거부터 봐서 쟤네부터 이렇게 마킹하는 게 방법일 수도 있어요. 스패닝 트리 알고리즘은 우리는 안 할 거예요. 근데 디작스트라랑 많이 비슷해. 디작스트라 한번 러닝하면 from single node to every other node 길이 다 나오잖아. 그치? 겹쳐지는 것만 좀 찝으면 비슷할지도 몰라요. So you can do this for your exercise if you wish. And minimum cost spanning tree, like he asked, they're saying that there may be a multiple spanning tree, but among those multiple spanning tree, I like to have the minimum cost ones. 6.4 actually give you one example, and it's all look like, of course it looked like a tree because it's connecting everywhere. One tree has a cost of 110, the other tree has a cost of 129. So please do take a look at 16.4 for your exercise. It's not that difficult. 그냥 그런 게 있구나. MCST라고 아무도 안 그러더라. Minimum cost spanning tree라 그러지. Or in some other graph, people, they call it different names. Sometimes they call it as a maximum cover, minimum cover. 또 좀 다르게 부르기도 하는데 그거는 우리 책에서 안 나오더라고요. 그래서 내가 일부러 얘기는 안 하고 갑니다. 나는 커버라고 배웠어. 스페닝 트리는 좀 이따 나왔고, 스페닝 트리는 이제 컴퓨터 관련 과목에서 나왔었고, 이것만 하는 수학하는 과목에 가면 또 다르게 불러. 커버라고 불렀던 걸로 기억해요. 맥시멈 커버가 뭐고 미니멈 커버가 뭐고. 그래서 커버 찾는 알고리즘 뭐 이런 식으로 했던 것 같아요. 다른 게 있다면 컴퓨터 과목에서는 알고리즘을 좀 더 집중을 하고, 그 수학인데 이런 쪽 하는 수학은 문제들이 그랬던 것 같아. 뭘 증명하라. 얘랑 이어지지 않는 걸 증명하라. 막 문제들이 다 이랬던 거로 넓히 기억해요. 뭐가 스패닝 트리가 아님을 증명하라. 맥시멈 커버가 하나임을 증명하라. 뭐 이런 문제들이 그렇게 좀 나눴던 것 같아. 같은 걸 가지고. 아이고. bipartite graph. 이거 anyone heard this bipartite graph? Bi, what does bi mean? We know what bi means. 둘, 1, 2. Bipartite. Partite maybe separate into two. Graph that you have node in two different sides. And some graph will be rearranged to be like this. Bipartite graph. A bipartite graph is a special type of graph where the set of vertices can be divided into two disjoint sets U and V. So left side of the node is U, right side of the node is belonging to some group V. Such that no edges have a both endpoint in the same sets. What does that mean? Such that no edges has a both endpoint in the same set. If you're in the same set, there will be no edges between them. You only have edges to the another set. Actually, you can change this graph to have a bipartite graph. So there are later algorithms like given a graph, decide whether this is a bipartite graph. 찾으라고. 그래프 준 게 bipartite graph인지 아닌지. How can you make a bipartite graph? A simple undirected graph G, V, and E is called bipartite graph if there is exists a partition dividing the two of a vertices set V, V1, and V2. 뭐 여기 있는 노드랑 여기 있는 노드랑 다 합치면 전체 노드지. That's why they say union, V1 union V2. And for both V1 and V2 are independent set, which means doesn't overlap. See? Read example 6.3 and 6.5. They try to give you a bit stupid examples. Like they wanted to assign a translator, interpreter with a different language. So it's a group of people. They speak all different language. All different language. One speak English, one speak Spanish, one speak Japanese. You only have a three translator. There is 10 people speaking all those languages. How can you pair them? What is a good way of pairing it? If you think about it, 3 translators this side. There is 10 customers here. This one speaks Japanese. Okay, so it's Japanese, Japanese, Japanese. English, English, English. Maybe there's 여기 English. And then there is one with the Spanish. This one maybe Spanish. Matching problem. They wanted to describe it into bipartite graph problems. So that's the example given in the textbook, and it's not that helpful, but it's a clear example of you can have a disjoint set like this. 왜 이런 걸 할까? 왜 그래프를 이렇게 다 만들었을까? 왜 모든 걸 그래프로 하려고 그럴까? 맞습니다. 이게 어느 정도 맞는 얘기예요. 문제가 복잡해지면 지금은 이렇게 몇 개 안 되는 얘기 갖고 하지. 몇 개 안 되는 얘기 갖고 하잖아. 그리고 뭐 인터넷만 해도 아까 뭐 조그만 그래프 그려놓으면 수십만 개의 노드를 연결하려면 이런 방법밖에 없어요. 그리고 이걸로 자기가 풀고자 하는 문제를 이렇게 표현을 하면 알고리즘을 짤 필요가 없잖아. 알고리즘이 이미 다 있는데. 그지? 알고리즘이 이미 다 있는 거 있으니까. 거기다가 이미 다 검증 다 된 알고리즘이 있으니까 그거다가 붙이고 나중에 내가 필요한 정보만 빼면 되니까. So it's another way of doing modeling, another way of doing abstraction. That's a power of a graph. Looking at every single problem into a graph, that is also a very powerful approach. Graph properties, number of edges, undirected graph. Each edges is a form of UV. U and V is not equal, right? I and J is not equal. If it's same node and the same edges, that doesn't make sense. So the number of possible pairs in the n vertices graph is, what is all number of all possible pairs in the graph? 뻔하지. n times n minus 1. 그치? 나 빼고 나머지들하고 다 짝을 맺을 수 있거든 하니까. 그지? 맞지? Since the edge U and V and the same edges and VU, that means it's an undirected graph. 그치? UV나 VU나 뭐 방향이 없으면 it's the same thing. So number of edges in that undirected graph, it should be divided by 2. So n times n minus 1 divided by 2 because it has no directions in it. It's a one edge anyways. Thus, number of undirected graph, number of edges in an undirected graph should be less than or equal to n times n minus 1 divided by 2. Make sense? 그죠? 말 되죠? 뭐 완전 유치원생한테 하는 것 같다. 그지? What about directed graph, number of edges in the directed graph? Number of edges in directed graph. Yeah. We could have a maximum of n times n minus 1 because all the directions. 이렇게 그리니까. 아까처럼 이렇게 그리지 말고. 이게 조금 애매한 것 같아서 이렇게 그리지 말고 one way. So should be less than or equal to n times n minus 1. Vertex degrees. Vertex degrees. It's the properties of the graph. Sometimes they use these properties to represent they come up with some new algorithms and stuff. So vertices degree. Degree of a vertices is a number of edges incidence on vertex I. So simply counting how many edges that I'm connected to. That's same as vertex degree. Same as no degree. 그치? No degree. Degree 2 is 2. Degree 5 is 3. Degree 3 is 1. Blah, blah, blah. We all know this. And sum of the vertex degree should be equal to 2 times all the number of edges. Okay, I think I'm gonna stop here today. 그만합시다. 마지막에 거의 끝나가는데.